This is Earth Science Lecture number 11. This lecture is on Uniformitarianism and the laws of relative age dating. In this lecture, we're going to look at the concept of geological time and the various laws of relative age dating listed as original or horizontality, superposition, lateral continuity, cross-cutting relationships, and inclusions. Geological time is basically a way of investigating the history of the Earth. We've talked about the Grand Canyon before in this class, and if you look at this picture, you could see various layers that are exposed as the Colorado River very slowly eroded its way through this region of the United States. Most layers that are present on the Earth are outside of our field of view. In very special environments, though, like where a river cuts a valley, we could actually see layers that are below our feet. And just like pages in a history book, each layer represents a certain episode in Earth's history, so it helps us to understand what the past environments and conditions were like on the Earth in the past. Very early views of Earth's early history were really not scientific. They were based on beliefs that there were large-scale catastrophic events that happened in the past. This field of view is referred to as catastrophism, and in catastrophism, the early views of Earth's age were that it was actually quite young. Earth was on the order of thousands of years old. This is a painting of Usher, who was the first person to really go through and determine the age of the Earth by going through generations through the Bible and figuring out, going back generation before generation, ultimately where you get to the oldest possible age that can exist. And so, in order to explain things on the Earth, such as a volcano or a mountain or a river valley like the Colorado River Valley that carved the Grand Canyon, if these features developed on the Earth, they basically resulted from very sudden worldwide disasters. A sudden worldwide disaster like a catastrophe. They were produced by unknown causes, and they really are no longer in operation today. So volcanoes, mountains, river valleys would very, very suddenly form from very catastrophic floods or huge events that we no longer see happening on Earth today. It was later that a person by the name of Hutton came along and really tried to estimate Earth's age, but in more of a scientific sense. Here's a painting of Hutton over here on the side. Hutton made this proposition in the late 1700s, and he came up with an idea, which is the title of this slide. It's called Uniformitarianism. What you might see in this term is the root uniform. Basically said, the present is the key to the past. The Earth has been uniform. The processes that formed the past landscapes, such as the processes that created a river valley or a volcanic landform or another kind of mountainous landform, these are the same processes that are happening on Earth today. Basically, found that there was no reason to think the early Earth was different than the current Earth. He actually scientifically observed these processes. He would go to the shorelines of Scotland. He was actually a Scottish person, and he would notice that the sediments on the beach were very similar to the rocks that were making up the cliffs along the beach. And so he tried to measure how long the process of erosion would occur. He envisioned that it was the waves that were eroding the cliffs, producing the sand that was on the beach that he saw. And he measured that the process of erosion was extremely slow. And so because of that, if you were to create all of those sediments that you observe on the beach, this led to his first estimates of Earth's age in a scientific sense, that Earth must be at least millions of years old to produce all the sediments that he saw. People then began to determine relative ages of layers on the Earth. Relative age dating is describing, if you see various rock layers, which ones are older or younger than other ones. So it's not an absolute age, it's not a numeric age. We'll see that later. It's called radiometric or absolute age dating. This is just determining if a layer is older or younger than another layer. And so you could reconstruct the geological history of an area by putting in a sequence of events. What happened first, what happened next, and what was the most recent event to occur. What was evolved from this field of view was something called the laws or principles of relative age dating. Scientists of the time, really beginning in like the early 1800s, put together these laws. The first one is called original horizontality. Stratigraphic superposition is the second law. The third law is called lateral continuity. Cross-cutting relationships is the fourth law. And the last law is called inclusions. So I'm just going to go through briefly what each entails, and we're going to spend a lot more time in lecture looking at these particular laws in some more detail. Now, original horizontality, looking at this, you might see the word horizontal. This applies only to sedimentary layers, so if you saw igneous or metamorphic layers, you wouldn't be able to apply this law. Basically, the idea is that if sedimentary layers are deposited and lithified to form a sedimentary rock, it's going to happen in a horizontal fashion. Just like when snow falls down, if you have a big volcanic eruption and the ash were falling down, or if you have sediments that are falling down in the bottom of the ocean, they're going to be forming flat layers. There's no way that you could get tilted layers like you see here in this picture. The orientation of these layers is really almost 45 degrees with respect to the horizontal. So what that implies is if you see sedimentary layers that are not horizontal, if you have sedimentary layers which are tilted, they're not original. Something must have happened to deform the layers. Could you think of a process that might tilt layers? Like here we see really folded layers on the side of a road. This is actually a road cut. So these lines that are going through the layers are the drill holes that the highway department used to put dynamite in and blast away at the side of a hill. And we could see the folding inside of that. I have an animation here which can illustrate what kind of environment you could create tilted or folded layers. If I have some layers which are compressed on either side, these big arrows are showing that compression, the layers can actually fold around. Now how that can happen? Well, we talked about plate tectonics earlier, and in a plate tectonic environment where tectonic plates push on each other, you could actually get folding. We're going to see that this is a process which creates mountains, and the type of plate boundary we'll see later on is called a convergent plate boundary. So the next law is referred to as superposition. Sometimes it's referred to as stratigraphic superposition. But superposition is the key word here. This also only applies to sedimentary layers. So you wouldn't use superposition if you're looking at igneous or metamorphic. Now, if you were to look at a sequence of sedimentary layers, like what are shown here in the Grand Canyon, the principle of superposition tells you that the layers which exist on the bottom are the oldest. They formed the longest ago. The sedimentary layers that are on the top of the sequence are the youngest. And so if you were to go to the Grand Canyon and descend down the canyon from the top, you're basically going back in time. The next law is referred to as lateral continuity. Now this also applies to sedimentary layers only. When you see sedimentary layers exposed in one area, this law helps you to infer that they don't just end abruptly, but they sort of pinch out and become thinner and thinner with distance away from where you are. So the law basically says that layers of sediment will not end abruptly in a lateral sense. Layers will extend horizontally as far as the sediment was carried by water and deposited, and they basically will thin out in a sideways fashion, in a lateral fashion. The fourth law is called cross-cutting relationships. And cross-cutting relationships refers to two types of formations that can cut across rock layers. The first formation is called a fault. A fault is something that happens when you have an earthquake. It happens in areas where you have plate tectonic activity. If you notice in this picture, there's layers on the left which have been offset from the layers that are on the right. There is a two-dimensional plane which divides these two groups of layers. The plane is going into the page, and that's basically where the two layers have shifted with respect to each other. It's like I took a knife and cut through and then shifted the two layers. And so that's a fault surface where one side moved relative to the other. So that's one variety of thing that could cut through layers. The second variety of thing that could cut through layers is an igneous intrusion. You could either have a dike, and here in this picture, remember, dikes are the ones that go up and down, or they go through layers in a vertical sense. You can have a sill, and sills spread out laterally between layers in a horizontal sense, or you can have a batholith. A batholith was the remnants of a very large magma chamber. When those igneous intrusions come up, they basically cut through everything in their path. So how cross-cutting relationships work is that the fault that you see is going to be younger than the layers that it cuts through. So what that implies is that the layers that this fault are going through, the green, the orange, the purple, the other orange, kind of yellowish layer, those layers had to be there first, and then the faulting happened. So the fault is younger than the layers that it goes through. Likewise with igneous intrusions, these are also younger than the layers that they go through. So the dike in the picture, the sill, the batholith, these all came after those layers, those original layers were deposited. The green, orange, purple, orange, and yellow layers were there. And this kind of makes sense because it's impossible to have a fault go through something if it's not there when the shifting happens. And so if you see faults in a picture, that tells you that they are younger than the layers that they offset. But if a fault doesn't go through layers, like here we have layer E, layer D, these layers have been offset by this fault, which is this kind of thick black line, which is labeled F. The fault goes through E and D, so that implies that E and D had to be there first, or E and D are older than the fault. But since the fault does not cut through layer C, that tells us that C came after F. So D and E are the oldest, then F happened, and the younger thing to occur was layer C. So the fault labeled F occurred after E and D, hence F is younger than E and D, but F is older than C. Now if you have an intrusion, so here there's actually two intrusions. It's very hard to tell from an illustration what the rock types are. So they've put little V's here to tell us that this is an igneous intrusion cutting up. We have a dike labeled P, and we also have a sill, which is horizontal and goes between the layers. It goes between L and N. And so these things have to be younger than what they go through. So that tells us that Q, O, N, and L all formed first, and then they were cut through by this dike and this sill. Since the dike and the sill don't affect layers H, I, J, and K, this tells us that those came most recently. So the intrusion labeled P occurs after Q, O, N, M, and L were deposited. So P would be younger than those things. But again, you could also use cross-cutting to say what a igneous intrusion or a fault doesn't go through. What it doesn't go through should be something that formed the most recently. The final law that we'll review is number 5, the law of inclusions. An inclusion is a broken off piece of one rock found within another rock. So in this picture you see this tan rock on the left, this kind of gray rock on the right, and there are little pieces of the tan rock within the gray rock. So we would call those inclusions. Now the rule for inclusions is that if you have two rock layers that are next to each other, but one has inclusions of the other rock layer within it, it tells you that the rock that broke to make the inclusions is the older one. So in this case, since the tan inclusions lie within the gray rock, the tan rock had to be older. And this also makes sense because if you think about it, the tan rock had to be there and it had to break apart to form those little pieces before it could be incorporated within the gray rock sample. So when we have our class on this topic, we'll complete a number of exercises where we will apply these laws, and it will definitely help you to remember them.